Hello, Chem 1211. We're going to talk about the mole, the concept we learned about last time, a way to count, essentially, and how they fit in with reactions, because our big goal now is to start to use the mole within the reaction scheme to kind of get things moving. So let's check it out. First off, just a reminder from what we talked about last time, and that this mole concept, which is really a measurement of how many packages we have of a certain size. So our package is 6.022 times 10 to the 23rd. Sure, it's an odd package, but it's the package we all deal with. And if we know that that's the number, that there's 6.022 times 10 to the 23rd of those things, that's Avogadro's number, we can convert from the number of packages to the actual number of things that we have. And so that's what we do. Whenever we need to know exactly how many things we have, we use Avogadro's number. This is an actual very rare transition. This right here, going back and forth right here, is very rare. We don't do that a lot. We're normally satisfied as chemists to talk about the mole. So that will become our lingo. Everything will be in terms of moles, but we have to understand that we can always go back to the actual number of things if we have to. Okay, so that's fine and dandy. Well, what about the other direction? At the very end of our meeting last time, we talked about the mole, and we saw that it could go from, we could use it to get to the mass of an object by using the molecular mass, which comes from the periodic table, or the atomic mass, which comes from the periodic table. Both of them do. So there's another one. This is a more common conversion because it gives us something we didn't have before, a way to go and measure how many moles there are by simply tossing something onto a scale and getting its mass. So if we measure the mass, then we have a way to get to how many there are by finding the number of moles and then using Avogadro's number if we want to know the actual number. We won't do that too often. We'll normally stop at moles. We could also go backwards, of course. If I told you how many moles there are, you could go back and tell me what the mass of that stuff should be. It's as simple as pie. The conversion factor is the molecular mass or the atomic mass, depending on whether we're talking about an atom or a molecule. So that's just a review of last time. Let's pick up from there and think about what a chemical reaction is telling us. So when we talk about chemical reactions, we need to learn to read them properly. So here's an example of benzene, C6H6, right here, okay, reacting with molecular oxygen, which is just called oxygen, and then it forms for us carbon dioxide and water. This particular reaction is a type of reaction called combustion or burning. So when we take something like a hydrocarbon, benzene, which is made of just carbon and hydrogen, and we react it with oxygen, that is actually what burning is. Whenever we see a flame and stuff like that, we're talking about burning like a piece of wood. We're burning something. It's the carbohydrate plus the oxygen forming for the main reaction is carbon dioxide and water. All right, so how would we read a balanced reaction like this? Notice real carefully that I have balanced this already. You should go back and double check to make sure you can do that because this is a skill we learned earlier and you are now expected to apply it. So if we read this on the atomic level, this says if you give me 2 of these benzene molecules and 15 of the oxygen molecules, so that's right, that's 2 of the benzenes, 15s of the oxygens, then I can somehow make these guys produce 12 carbon dioxides and 6 waters. So if you give me 2 molecules, 15, I can make for you 12 and 6. Okay, and the way I'm going to do this, I have to rearrange and break bonds and make new bonds. You can imagine a whole bunch of molecular model kits sitting in front of us, 2 benzenes, 15 oxygens. We'd have to break some bonds and then put them back together to make the bonds. Something that might be worth seeing someday if you ever get the chance to do that. But the fact of the matter is, this is the atomic level viewpoint right there, and most often we're not going to use an atomic level. We're going to want to talk about things on the mole level because that's where we get macroscopic versions of our reactions. So instead we would say something like this. If, and I'm going to erase up here if I can get my thing to erase, there goes that. All right, so it's going to erase here any second. I'm certain of it. All right, good. So if you give me 2 moles of benzene and 15 moles of oxygen, then I can make for you 12 moles of CO2 and 6 moles of H2O. So in other words, these stoichiometric coefficients, the numbers that we use to balance, they represent either the number of atoms or the number of packages that we need. 2 moles, 15 moles. Those are our packages of those things. As long as we talk about the same consistent unit, moles or molecules or atoms, we're going to be safe in that we can do this, that we can make this kind of discussion about a reaction. And this is the first step to understanding how we're going to do our calculations. Now, I want to make a real important note. Nothing in here, not once have I talked about the mass, because the mass isn't what's important. What matters is how many things we have, not how much they weigh or what their mass is. For example, if I tell you that I'm making something like a car, and I tell you that it requires 4 tires and a frame to have a car, you'd say, oh, well, they don't have to all be the same mass. I don't have to have 500 pounds of tires and 500 pounds of frame. I need maybe 100 pounds of tires and 1,000 pounds of frame. So the mass isn't what matters, it's how many that we need. So let's see why that's the case by building this up into like a little picture view to get some intuition. So consider this crazy reaction, and we'll be doing this a lot now. We'll be making up just generic reactions. 2A plus B goes to A2B. Now these aren't real, and it's just an idea, and that's all that matters. So we're making 2 molecules or 2 atoms of A, whatever A is, react with 1 molecule or 1 atom of B, and we're going to make 1 A2B when we're done. So we could, if we wanted to, we could have put little stoichiometric coefficients here, but remember, no one does that. They always leave out the ones. So we're going to continue to leave the ones out here. Now, we can imagine this reaction as a before and after scheme, a before and after scheme. And so I want you to think about it that beforehand, we're going to put in our reactants way over here on the left, our reactants, and we're going to make our products over here. We need to know that terminology. Reactants are the before, products are after. So this is reactants, just to remind you, reactants, and this is products. So if we imagine our reactants over here, then from this picture that we have, we might be able to glean what's going to happen afterwards. If we imagine everything happens as it should be, if this reaction describes what's going to actually happen, then what can we do to kind of predict what's going to happen here? We want to know what's going on inside this, what's going to be there after the reaction's done. So to help us, I'm going to kind of clear this stuff, clear the air a bit, get rid of some of these things so we can focus on just what's important to us, and that is the reaction itself. I was hoping to get rid of these lovely yellow spots, but they're not going to go away, it doesn't seem. All right. Anyways, so let's focus on this. 2 A's and 1 B are needed to make the product. So what I'm going to do is I'm going to take this red thing and I'm going to circle 2 A's and 1 B. So this says if I have 2 A molecules and 1 B molecule, I will make an A2B. So over here, I'm going to make an A2B out of that group. Now I'm going to circle another set of A, and B, which will make for me another A2B. And then finally, I'll circle the A, and the B, making another A2B. So what we've just learned is that for when the chemical reaction occurs, these clumps that they talk about here, okay, the stoichiometric coefficients actually manifest themselves in how many we pull out from the reactants to make the products. Let's try this again with a different amount of stuff in there. See how that works. It's going to take a little bit of work, but we'll do it. All right, so what we had before somehow made 3 A2Bs. Let's try this again. Let's put an A, an A, an A, an A, an A, and a B, and a B in here. Now let's see what happens. All right, you can imagine that if this was to occur, every two A's, an A and an A, would react with a B. And the same thing would happen right here. An A and an A would react and form a B. So we'd have, if you think about this, we'd end up with two A2Bs, but we'd also have, look at what's left over right here. This guy didn't react. We had too many A's. That's okay. This just means we ran out of the B's first. All right. Well, next time, when we do this next time, we're going to talk about this. This B, this leftover A tells us that we ran out of the B's first, and therefore the B was what limited how far we could go. So we'll give that a whole name. We're going to do a whole day talking about that. For now, though, we would just write in here that there'd be two A2Bs and an A still left in the container. All right, let's try it a little bit differently. Let's do another one. Let's imagine instead that we had this set up. We had 2 moles of A and 2 moles of B in the container. We no longer just have individual atoms or molecules. We have huge collections of A's and B's. But since they're both in the same unit, collections, these same unit of collections, a mole, it's pretty easy to say that the way to go about this would be to let's kind of simplify this and say we have a mole of A and a mole of B, a mole of A, and another mole of B here, and a mole of B. Just to remind you, once again, you can use mole with an MOL or MOLE whenever you do this kind of work. If we do it this way, then we have to remember that these things, these stoichiometric coefficients, can represent moles as well. So we can circle 1 mole of A, another mole of A, that's our 2 moles of A, and then 1 mole of B, and we would then get 1 mole of A2B, and what's left over? 1 mole of B. Now, many of you are seeing this. It seems so obvious to you. You're thinking, why is he going over this? This seems way too easy, while others are still a little confused. This is a tricky business, and we want to be able to do this kind of stuff for more complex arrangements and from different starting areas. So for now, I'm going to do one more example just for fun, and then we're going to move on and learn how to use this a little bit more fluently without drawing pictures and all this stuff. So let's do one more example. Let's do, how about, let's do 5 moles of A. So that's going to be a mole of A, a mole of A, a mole of A, a mole of A, better put that A there, and a mole of A. And we'll put a mole of B here, and a mole of B here, and a mole of B here. So now let's go ahead and do our normal routine of 1 mole, 2 moles of A, that goes right there, and 1 of the moles of B, I'm going to get one of these guys. I'm going to get a mole of A2B. Then I'm going to go up here and I'm going to circle again a mole of A, and a mole of A, and a mole of B, and I'm going to get another mole of A2B. But now the question is, what can we do with what's left over here? Now, if these were just molecules, okay, or atoms, we'd be stuck. We don't have enough A's to make a B if they were molecules. But a mole is a whole bunch of these things. So we have the ability to have half of a mole. We have the ability to have half of or a quarter of a mole. Well, we don't have the ability to have half of a molecule. That doesn't make any sense. So what this means is for every 2 A's, we need 1 B. That means it's a ratio of 2 to 1. So for every 1 A, we need half of a B. So another way to state all this is, for every 1 A, we need, that's 1 A. For every 1 A, we need half of a B. If that's the case, we could make another, are you ready? We could make another half of a mole of A2B. Now, if this one doesn't make sense, oh, and by the way, that's going to leave us with a half of a mole of B left as well. So this last example is pretty complex, but We'll be able to do this mathematically in just a minute, so it won't be a big deal once we get away from the picture and just learn how to do it mathematically. So hopefully you're following. If not, well, we'll see if we can make sense of this as we move along. So here we go. Here's our reaction that we've seen. 2 moles of benzene, 15 moles of oxygen, 12 moles of CO2, and 6 moles of water. Okay? What we just learned was if we know something about how much we use, it's going to dictate how much of this stuff we need, how much of this stuff we need, and how much of this stuff we need. So we can actually think about these as relationships, just like I wrote above. It's telling us from the stoichiometry that for this particular reaction, this relationship right here is true. Anytime you have 2 moles of benzene, you're going to be using up 15 moles of oxygen. Every time that you use 2 moles of benzene, you'll be making 12 moles of CO2. And every time that you use 2 moles of benzene, every time you use 2 moles of this stuff, you're going to make 6 moles of water. All these numbers came from the balanced chemical reaction. Now, the important thing is these are just equalities or relationships, and our relationships can be turned into conversion factors with ease. If you remember, we did that back in chapter 1. These are just conversion factors which we can read right off of the reaction. Okay? Let's see how that plays out in 3 example problems. We're going to use the same reaction, okay, that we just talked about. 3 example problems to get our chops all going on this. So let me write the reaction here. Once again, it's 2C6H6 plus 15O2 goes to 12CO2 plus 6H2O. All right, so here's our 3 problems. First problem, if we have this many moles of benzene and we burn it, that's the reaction we're talking about, right? The burning of benzene. How many moles of carbon dioxide are formed? So what are we looking for? Remember, you need to follow this format. You need to tell me what you're looking for. You're looking for the number of moles of CO2. That's what it's asking for right here. How many? There's the question mark. See it? Look for that and then read backwards and see what's there. How many moles of carbon dioxide are formed? We're looking for the number of moles of CO2. What do we know? All we know about is the number of moles of C6H6. Now, these little labels are important. You're going to need to keep those on there to keep track of things. Don't leave them off. All right, what do we know from our chemical reaction? Well, according to this, for every 2 moles of benzene, I can make 12 moles of CO2. In other words, for every 2 moles of benzene, okay, I put the benzene in the denominator so that the moles of benzene would cancel. I can make 12 moles of CO2. And lo and behold, if I do my math, it's going to be 6 times 8.78, and I'm going to get 52.7 moles of CO2 can be formed. Now that seems like it should have been very hard, but it was very easy. We knew this relationship right here because it came from the periodic table. I'm sorry, not the periodic table, from the balanced reaction. From the balanced reaction. We'll get to one that uses the periodic table later. All right, let's do another example. See if this can start to make sense. Hopefully it is. We're just going to keep using the balanced reaction to do this. And we're in moles right now. So let's see. It says if we have 57.55 moles of water, if that's what's formed, how many moles of oxygen were used? How many moles of oxygen? So we're looking for the number of moles of O2 that were used. What do we know? 57.55 moles of H2O were formed. Do we know a relationship between H2O and oxygen in this particular example? The answer is yes. We know that for every 6 waters that were formed, we needed to use 15 oxygens. See, it's sitting staring you right there in the face. It's right there in the balanced reaction. For every 6 moles of water we formed, for every 6 moles of water that we made, we had to use 15 moles of O2. I put the moles of water in the denominator so that they would cancel out with the moles of water I already had. If I take this, I'm going to get 57.55, multiply by 15, divide by 6, and I've got 4 digits, so 143.9 moles of oxygen were used. Now notice, I've circled my answer. You've got to get in the habit of doing that. All right, that is very important so that I know what you want me to give you a grade for as you do problems like this. All right, one more example problem, and it's more complex, where you're going to use the same reaction, but in this case, we're going to introduce a new term, and we're going to start with mass instead. So let's read this. In excess oxygen, excess just means we've got so much oxygen around, means so much we're never going to run out. So much O2 will not run out. Okay, that's what excess means. We got so much of it. We're going to burn 100 grams of benzene. The question is how many grams of water are formed? So we're looking for, in this case, something a little bit different, the number of grams of water. Number of grams. Well, that's fine. We've got the mass of benzene here, but we don't have a relationship between mass of benzene and mass of water. What we do have is a way to go from the mass of benzene, the mass of C6H6, and turn that into the moles of C6H6. Because once we get to the moles, I can go from moles of benzene to moles of water with ease. There's a 2:6 ratio there. So let's go back and try that out. All right, so I've got 100 grams. Turns out that benzene is 78.12 grams per mole. So that's grams of benzene per mole of benzene. 78.12, that's correct. So I've gone from grams of benzene to moles of benzene. Now that I'm here, and by the way, where did I get this information? This I got from the periodic table. Now I'm in moles, and what I know from the reaction is for every 2 moles of benzene, that's the same thing as having 6 moles of water. So the moles of benzene cancels the moles of benzene. Where did I get this? From the balanced reaction. And finally, I need to go from moles of water to grams of water. Well, it turns out that for every 1 mole of water, that's a mass of 18.02 grams of water. Where did I get this information? Once again, from the periodic table. That's just the molecular mass. Okay, this is the molecular mass. A molecular mass. Ooh, don't know what just happened there. A molecular mass. This is a molecular mass as well. These are stoichiometric coefficients right here. So if I do the math on this, I can find that I take 100 grams, 4 significant figures. I got 4 all the way across the board, so I can have 4 when I'm done. I do my math. I end up with, I am going to make 69.20 grams of H2O. And that's it. Hopefully this will get you started. We're going to do problems like these last 3 all class. Okay, maybe a couple like the very beginning, but for the most part, it's going to be a bunch of problems like these last 3.